So here we have 5.1 lesson. So we have a reaction between acetic acid and sodium hydroxide. We know that that's a strong base and all the hydroxides will come off. And for the purposes of pH and so forth that we're going to be figuring later on, we can ignore the Na plus, can't we? So here's the net ionic equation. And so let's go on to part B. If we had this much of the acetic acid and this much of sodium hydroxide, what we've got is an acid. It's not a strong acid, but it does have an H on offer, and that is a very strong base. That OH minus is a real acid chewer. So when we do liters times molarity and get moles, and liters times molarity and get moles, what we've got then is this reaction. Let's write it out again. We started with this amount of moles, don't we? This is the amount of moles for this, and this is the amount of moles for the hydroxide. And one of these will chew up one of those. And they make the point down here that when one of them is strong, in this case the base is strong, we can consider that the neutralization reaction goes to completion. We don't need to fuss around with K or something and say, well, what portion of the OH minuses will react? The answer is all of them. Let's just use all of them. For all practical purposes, it's all of them. So 0.03 of these will chew up and react with 0.03 of those, which is why that's the amount disappearing here. So this amount will use up the same amount of this chemical, which means that they're all gone because we used them up making these. Now, I don't care about the molarity of water and the moles of water, so let's just put an X there. But when I have effectively, let's just put the decimal here for a minute. If I have 4 of these and 3 of these, then 3 of these uses up 3 of those and leaves me 1 of those. That's the kind of ratio I'm talking about. Now, this is all gone, so I have 0 of this. And one of these reacting with one of those makes one of these. So it generates the equal amount of moles there. So this is the amount I have at the end of my strong base, weak acid reaction. Now, here's a wrong idea that I went on to some length in a class. And they make the point that this is not the final reaction mixture because the buffer solution needs to go to equilibrium. And that's true. I mean, what are the odds that we happen to generate just the right amount to have set up an equilibrium right there, dead on? I mean, it's pretty poor. So this is probably not true that Q equals K, and this is probably not the final exact amount that you will settle it will settle for equilibrium. However, you can't just take this amount and put it to the first power and over this amount to the first power and get Q. Now, another little point that will come up is I'm going to point out Q is dependent on molarity. And so if we're going to do this, we're going to try to use molarity, we got to divide by the new 70 milliliters, 30 and 40 milliliters, which is 0.07 liters. But I have to do it in both places. And since I'm using a fraction over a fraction, the bottoms of each fraction will cancel out. So when you have one of these reactions and you need molarity, but they're both in the same beaker like this, then you can just disregard the liters because it would have canceled out anyway. You don't even need to go find out what it would have been because it would cancel out. Then we can have the E negative 3 will also cancel out, and I just get 3. However, this is not Q in reality because this is not the reaction on offer anymore. What we've set up is, remember, we lost all the OH minus. What we've got now is this. I've got some of this and some of this in water. And what happens when you have that? Well, some of the HAC acts as an acid and it makes more of that, right? And it makes H plus. But I already have some of this, you say. Yes, we do. So we started with this, we started with that, and I got these numbers from here. Some of this will get destroyed, making some more of this, and some of this will get generated, the same amount. So I'll lose a little bit. That same amount will get added here, and that same amount will get added here. But if this started effectively at 0, because I'm only dealing with the amount that I had from water, from the natural dissociation of water, and I don't really care about that number because it's so small, so I'm going to call that 0. So this is my equilibrium numbers, and then I can put this in to Ka. In with Ka, and products over reactants to the power of the number in front, and this is Ka because I looked farther down the page, and this is the Ka for acetic acid. Here's the thing though, I can cross out plus x and minus x because Ka is 3 decimals or more smaller than the molarities at hand. And so do these numbers change? I just said they didn't. I just said that change in them is immaterial mathematically. Let's ignore it. Well, then how can it shift? How can it achieve equilibrium if these don't change and Q is not K probably, right? The answer is because it's going to generate some H plus or hydronium H3O plus if you like. And this amount is going to come up from being 0, and it's not going to be a big number, but it's going to be the proper number that when we multiply this fraction, this decimal, small decimal, times this, and divide by that, we do get K. K is a law of nature, and when you get an equilibrium, K is true. So you give this stuff, and this is done, you give it a shake and so forth, and you will set an equilibrium, set up an equilibrium, but not by changing this so much, but by generating enough H plus that this mathematically is small enough that multiplied by this, divided by this, will generate K. That's going to come up again on 2B, by the way. So what was the limiting reactant? Well, it's this one because it ran out, didn't it? And this is a buffer solution. We have a weak acid and the conjugate base, or we have a weak base and the conjugate acid. Either way you want to define it, it doesn't really matter. And the point of a buffer system is that the pH is kind of hard to push around, because if you put in some acid, you've got some base to react with it. You put in some base, you've got some acid to react with it. And so the pH doesn't just yo-yo up and down like it would in sort of a normal situation or a normal solution. And that's the point of a buffer, is it's pH movement resistant. Now, for example 2, let's talk about this amount, the molarity of sodium hydroxide and this amount of molarity acetic acid. But for part A, no NaOH has been added. Okay, so let's just deal with it with no NaOH. We just have this acetic acid. And in that case, what matters is the molarity. If we're not going to deal with a reaction with another chemical, and we're just going to deal with the acid nature of the acetic acid, then I don't need to know the amount. I just need to know the molarity. So this is going to start off at 0.1. We have none of this and none of this. We lose some, we gain exactly the same amounts. We lost this and we gained that. So Ka is 1.8 e negative 5, and it's equal to products over reactants, all to the first power, except that Ka is small enough I can cross out x, and we generate x, which is H plus. Notice it's H plus, and I wanted pH, right? Find the pH of the solution. So I can take negative log of that and get pH. Now, I also want to talk about some mental math here, because I can take a pretty good whack at finding this answer, and I don't even have to use a pencil. Once I set this up, I'm going to multiply by 0.10. Well, where does the where does the exponent move when I multiply by 0.10? When I multiply by 0.1, the number has to get smaller. So does this exponent go to negative 4 or negative 6? Well, negative 6 is smaller. So this is now 1.8 e negative 6 when I move this over. And then I have to take the square root to find x. And I find out a lot of kids have not been taught this part. Ignore these numbers just for a moment. Let's pretend they're not there. When we multiply numbers of a common base, we add their exponents. So to find the square root of 1 e negative 6, and somebody's shouting, it's not 1. I'm just going to do the e number first. What if it was 1 e negative 6? What would it be? What would the square root be? I need two numbers that are identical, and the exponents on the common 10, the exponents must add to negative 6. What's in the box? What's the exponent in the box? And they must be the same. It must be negative 3 as the exponent. So square root of 1 e negative 6 is 1 e negative 3, or 10 to the negative third, same thing. So square root of this part now is 10 to the minus third. And this is almost 2, and square root of 2 is 1.4. So this is a little bit lower. It's kind of like maybe 1.3. Ding. It's 1.3 e negative 3. Now, the other thing to watch out for, and they really do this on the test occasionally, is they set you up so you need to write it out as an acid equation, or they've written it out as an acid equation, but what they've handed you is Kb, or they've written the base and you need Ka. Now, we need Ka for this, right? Just pretend they had given us Kb just to be difficult. This is how we would generate Ka, because this times this must generate, this is Kw. This is the K for water. Now on part B, let's add 10 milliliters of NaOH. Okay, so all the OHs come off, and that's the part I care about. So let's get the moles, not the molarity, for both reactants, because this is what we've got going on now then, right? Take a look at that. Liters times molarity is moles and moles, and so that's where I got these numbers. This means millimoles, which means 10 to the negative 3. So this isn't 4, it's 4 e negative 3, or also called millimoles, because milli means 1,000th. So what happens? Well, again, one of these will burn up one of those. So if I have one of these, it burns up one of those. That's where this, why I'm subtracting this out. That's where that went. And that's what gives me 3. This is all used up, and this started at 0. So I end up with 1 e negative 3, to be picky, moles of the anion. The water is immaterial. Let's cross that out. Now we have a buffer solution again. We have a weak acid and the conjugate base. What is the pH? Now, there are 2 ways to do this, one of which is the Henderson-Hasselbalch reaction, which I recommend you memorize. It is in the booklet, but that kid who gets a 5 is going to know this. The difficult part for me was always remembering which one was on top, the base or the acid. And I finally decided this looks like a pyramid, and now I know which one it is. It's kind of a dumb method, but now I remember that my smaller one, the A- goes on top. So we said, remember that the Ka for this acid is so small that we can essentially say that this amount in this amount are not going to change. What's going to happen to the moles of those? Essentially nothing. Now, this is molarity, see the brackets. And I technically, to be super picky, have to divide each of these, because this is moles, by the milliliters, which is 10 and 40. So I have to divide by 0.05 liters, divide by 0.05 liters, but that's going to cancel out. So there's no point in it. Because they're in the same beaker, when I've got a fraction like this, it's just going to cancel out. I don't even have to go look and find out what the liters would be. I know they're going to cancel out. Dividing by liters to get molarity will just cancel out in this case, because I'm going to use them directly over each other, and there's no plus X or minus X and anything like that. So there's mathematically no point. So what I need is pKa. P number is the negative log of the number under discussion. So the negative log of the Ka got me that. Log of 1/3 is, I forget, some amount, add them together, and they equal pH. Now, I went and did it another way, just to kind of prove that you could. We now know that since this is gone, as I said back up on example 1, that what I've got is this going on. And I wrote it out this time the more official way, with the hydronium being generated in the water as a reactant. So we know that really the moles are in 50 milliliters of water, right? Or 0.05 liters and 0.05 liters. And so this is the molarity and this is the molarity, really. So K will be equal, Ka, because this is an acid reaction, Ka will be equal to products over reactants to the power of the number in front, except remember, this is going to be losing some amount. This is going to be gaining some amount, and that's where I got these. Except we said Ka is so small that plus X and minus X doesn't really matter, so we can cross them out. So when I take this, also reduces to 1/3, and when I divide by 1/3, I get this, and that is X, and X is H plus, or H3O plus, and negative log of that will give me pH. So you can do it either way. Also, I will point out, again, because these are in the same beaker and it's just a simple ratio like this, because we're going to cross out the X and minus X, the plus x and minus x, I could have skipped this part because I could have said 3 over 1, and look, that boils down to 3 over 1. Excuse me, it would be 1 over 3. 1 over 3, and this is 1 over 3 essentially. So I don't really have to divide by the liters. I could have just skipped ahead with the moles in this case, because I'd be dividing by the same number in both the numerator and the denominator of this fraction. I went then and also solved it as a base, just to prove to myself that we could do that. I said, you know what? There's no reason to assume automatically that this is an acid reaction now, right? Because I've got some of the base and some of the acid. So I turned it around and I went and solving it. Here's my moles, and here's my moles. This is millimoles, I guess, if you want to be picky, and millimoles. And I had to go get KB, so I did that by dividing it into KW. Now I have KB, and I have my products over reactants, the power of the number in front, except I'm going to be gaining on this one and losing X amount on this one. But you know what? It's immaterial. Let's cross those out. So we get 3 times X. So I divide by 3. Here I get 3X, divide by 3, and I get X. But what is X? X is the OH minus. So I took negative log of that answer. And I get POH, and 14 minus that answer is 4.27. So close as to be essentially the same thing. You can solve it this way too. I want to go back and point out something. The K for this reaction is not going to be KW over KB. I thought it was, and I had to go ask a question, and it was pointed out to me that this is not the action of the acid in water. Okay, so this is not true. We are not going to get the K for this reaction by taking the KB here from the reverse version and then dividing it into KW. So the K for this is not 1.8 times 10 to the negative 5. It is not taken from down here because this is the acid just in water. Remember, the real version would have plus H2O, and this would be H3O plus. This is the action of the acid in the presence of hydroxide. If you flip this around, this is the action of the acetate ion in water, and it generates OH minus. This is the literal reverse or inverse version of the acetate basic ion, the ion that is basic, that is a base. It is not the action of the acid in water. So the K for this is not 1.8 E negative 5. It's 1 over, as I recall, 5.56 E negative 10, which means it's extremely large, which is another way of saying this goes to completion, which is what we said, which is what the text says. On C, again, liters times molarity is moles, and it turns out we have half as many moles of base as we do acid. That means that when we put it in our little ice box here, it's sort of an ice box. Anyway, this amount will chew up half of that. So half of this gets converted from this to this, and all the base is gone. So none of it remains. What we end up with at the end point here then is an equal amount of weak acid in the conjugate base, which is the standard sort of version of a buffer. And very significantly, pay attention, is the half equivalence point. And the College Board loves this. It's almost got to come up on your test at some point, even in a multiple choice problem. And I'll show you what I mean here. If you have equal amounts of this, then in the Henderson-Hasselbalch equation, remember the base goes on top, but it doesn't really matter because they're both the same number. And you don't have to divide by the liters because you would be dividing by the liters in both cases, the same number, top and bottom, so it would cancel out, so you can skip it mathematically. Remember, millimoles is acceptable because the liters would just cancel out. So what we get is a fraction that's 1. Log of 1 is 0. This whole thing turns into 0. And pH is simply pKa. And it really might turn into a multiple choice problem, if nothing else, where they kind of just hand you the information that you're going to be using 0.2 moles of 0.4 moles of this and 0.2 moles of this. And you're supposed to be able to say fairly quickly, and I mean like inside a minute, wait a minute, this is going to chew up half of that. Half of this is going to convert. Oh, I have equal amounts. I have hit the half equivalence point, and I know, because I was paying attention, that at that point in the Henderson-Hasselbalch equation, this fraction is 1, log of 1 is 0, and the pH is the pKa, which they probably would have stated previously in the problem. And the whole thing takes you 40 seconds if you're doing real well at it anyway. It's probably in the test somewhere. I would rerun this until it makes sense to you. On D, liters times molarity is millimoles, and so 3 millimoles of this will chew up 3 millimoles of that, leaving 1, leaving 0, making 3, and you put them into the Henderson-Hasselbalch equation. On E, what happens if you give equivalent amounts? You've hit the equivalence point. Well, none of these are left. And you have only this. At this point, you do not have a buffer because you used up all your weak acid. So what you have then is only a base in water, a weak base in water, in which case you need the Kb because you have a base in just water. You're going to find the Kb from Kw over Ka. So you get that. Here's the equation written out. The weak base in water, it generates OH minus. So remember, this is the acetate ion. This is the acetic acid created, and this is OH minus. So we can put it into our K expression, products over reactants to the power of the number in front, except that minus X isn't worth it because Kb is so small compared to the molarities involved. So we can get rid of that. Solve for X, but X is OH minus. They want to then proceed like this, which I admit works. It's not the way I would have done it, but they point out that H plus OH minus molarities must equal Kw. Therefore, if you know one of them, you can divide it into Kw and get the other one. So that's what they did. And then they get H plus equals this. Negative log of H plus is pH. I would have said probably negative log of this is POH. 14 minus that is pH, but it's a style choice. You should get numbers that are so similar that it just doesn't matter. On F, we turn things around a bit because we make the weak acid be the limiting reactant. And we're going to run out of it, and we're going to leave OH minus in the water. And we're going to, of course, create this much weak base because all the weak acid got turned into the conjugate base anion here. So the HA is the limiting reactant. So what would be the pH at that point? Well, what we have, remember, we can cross this out. What we have is this and that. They are the reactants, essentially. Except in the idea of creating pH, this is so much worse at affecting the pH than this is that we're going to effectively ignore it. Let's ignore the anion as a base because Kb is too small for this to make a noticeable effect on pH. So I'm going to mentally cross this out. And remember that it was in the E minus 10 range. That's ridiculous compared to OH minus. It's not even worth considering. So what I'm going to do is just take the molarity of the OH minus, and I'm going to use that to figure the current pH. Once this gets done, it's at the end of this reaction. The OH minus molarity is the millimoles over 100 milliliters, because remember we added 60 milliliters to 40 milliliters. So here's the molarity of the OH minus ion, which means POH is 2 because we have 1 times the 10 to the minus 2. And then you could say pH is 14 minus 2, or you could do it this way. This is a little confusing because it looks like it jumps from here to there. H plus is then Kw divided by OH minus, in which case you get this, and then you need negative log of that answer, pH equals 2. So you get the same answer either way. So here's our sort of standard titration graph, and we generated that using the pHs we figured out. Here's our half equivalence point, and here's our equivalence point that we got in part E. And something to note is that, remember, pH is a logarithmic scale. So you have to add 10 times as much to push the pH farther from 7. Or to turn that concept around, you only have to add 1/10 the amount of the reactant, in this case the base, to push the pH through one more pH integer toward 7 as you approach 7. So this gets easier and easier to push the pH around, and as you get close, it just skyrockets. And this is, by the way, why the phenolphthalein indicator works, even though it is a little weird at first that it doesn't turn until something like 9.2 or something. But the difference between 7 and 9.2, or whatever it is, in the amount of base that you add in your titration is so little that you can still get results. That one drop, that last drop of base, probably took the pH through this whole section, like from here to there. And so your numbers in your math calculations are still pretty good. I would learn to recognize this titration graph. This is really classic. And if you're starting at a low pH, you must have started with the acid and you're adding the base, just in case something is a little confusing. I know it says NaOH added, but in case something didn't, we're starting at a low pH, aren't we, and not a high. If you add the acid to the base, then it does this and it dives downward and then flattens out.